This is a square, 1 unit on every side. Simple question. How long is the line straight across it, corner to corner? The diagonal. Sounds easy. It's actually one of the most influential questions in the history of mathematics. So, how long is it? Here's my favorite way to see it. Take 4 copies of our square. This little square has a side of 1, so its area is just 1. And the big one is 4 identical copies of it, so its area is 4. Now draw the diagonal across each, all leaning toward the center. And there it is, a tilted square, right in the middle. Each of its sides is one of those diagonals, length d, so its area is d squared. And the diagonals cut everything into 8 equal triangles. 4 make the tilted square, 4 make the corners. So the tilted square is exactly half of the big one. And half of 4 is 2, so d squared is 2. That's d squared, but what we really want is d itself, the length. What number multiplied by itself gives 2? Could it be a whole number? 1 squared is only 1. Too small. 2 squared is 4. Too big. So d is trapped somewhere between 1 and 2, and there's no whole number left in there to try. If it's not a whole number, the natural next guess is a fraction, 1 whole number over another. 3 halves? Squared, that's 2.25. Too big. 7 fifths? 1.96. Too small. So, do we just keep going? Fraction after fraction. Forever? There are infinitely many. Here's a sharper move. Instead of testing them one at a time, ask a single question. Are there whole numbers, a and b, whose ratio, squared, is exactly 2? Clear the fraction, multiply both sides by b squared, and it becomes a squared equals 2b squared. So suppose such a pair really exists, and take the smallest one there is. Geometrically, here's what it's saying. Start with a square on the side A. Its area is exactly 2 squares on the smaller side, B. Now slide both B squares into opposite corners of the big one. And 3 new squares appear. The middle, covered twice. 2 corners, not covered at all. The 2 B squares fill the big one exactly, so the middle they cover twice must equal the corners they leave empty. And you can read the corner right off the figure. It's the side A, minus the smaller square B, a minus b. The yellow overlap, side 2b minus a, holds exactly the area of the 2 red corners. In symbols, 2b minus a squared equals 2 times a minus b squared. But that's the same equation, in smaller whole numbers. A smaller solution, hidden inside the first. And there's the trap. We took the smallest pair, yet here's a smaller one. Impossible. So no such pair exists. No fraction squares to 2. So let's go right back to the unit square we began with. It's diagonal, we still can't put a plain number to its length. All our proof pins down is its square. D squared is 2. But don't mistake that for the length not existing. It's right there. You can draw it, run your finger along it, see it. Why can't we just say what it is then? The trouble isn't the diagonal, it's our numbers. No whole number, and no fraction, will ever land exactly on this length. So we give it a name of its own, the length whose square is 2. D equals root 2. And a number like this, that no fraction can name, has its own name too, irrational. A line you can draw in a second, whose exact length no fraction will ever pin down. From nothing but a square, living proof that not every number is a ratio.